Welcome to your last video of the week. I hope that the Chapter 8 test went okay, and I hope to see you guys on Monday. Go ahead and take out your notebooks if you haven't already. I want to talk about the start of Chapter 10, and start of Chapter 10 starts talking about circles. And the first thing we want to talk about is the properties of tangents. Now, it's not quite the tangent that you know from trig, but it is something that's similar that we'll go ahead and make the connection next week. But for right now, let's go ahead and keep them separate. That tangent function and trig is something very separate from what we're going to be learning today. So 10.1, use properties of tangents. There's a lot of vocab here that I want to go through. Some that you're going to know, some that you're not going to know. And the first thing I want to do, and again, just like we've done in videos before, if you need to go ahead and pause this video to make sure you get everything down, please do that. The first thing I want you to do is write down or draw down this circle as well as all of its different kinds of pieces. The first one is a chord. Then you also have the red radius. You have the blue diameter, and you have the center of the circle. Those are 4 words I do want you to know. I'm going to define them momentarily, but please make sure that you draw that down. First, a circle. What is a circle? Okay, we all know what a circle is. We've been drawing it for a long time, but by definition, what is the definition of a circle? Okay, the circle is a set of all points in a plane that are equidistant from a given point called the center of the circle. So if you think about it, if I draw some kind of random circle, if I'll do it right up here, here's my center and here's my circle around it. I know if I draw if I say here's my point on my circle, I know it's that far away from the center. If I draw this one, I know it's the same distance to that point. If I draw another one, it's that distance away. If I draw another one on the circle, it's the same distance. It's the same distance, the same distance, same. Okay, and so realistically, a circle is made up of an infinite amount of points that are exactly the same distance away from a center of a circle. Next, we should know this one, a radius. This is kind of a wordy radius definition, but it works. Okay, a radius is a segment whose endpoints are the center of the circle and a point on the circle. So again, if you were to look at the little circle that you've already drawn down, if I start at the center of the circle, I'm going to color it red, and I go to the edge of the circle and draw another point, you can see the endpoints. One is the center of the circle, and one is a point on the circle. Okay, that's considered the radius of the circle. The distance from the center of the circle to any point on the circle is what we call the radius. Going hand in hand with that is a chord. Okay, a chord is something that we probably haven't talked about a whole lot. Okay, a chord is a segment whose endpoints are both on the circle. So where a radius has a center of the circle and an edge, so it starts at the center and goes to the edge, you can see up on the picture that a chord is simply one that goes from edge to edge. Okay, well, it starts way over here and it goes all the way across to this over here. Okay, and you can go ahead and make an infinite amount of these chords. I can make another one down here from here all the way over here. Here's another chord. Okay, it just starts and stops physically on the circle itself. And then the cool thing is that we also have a diameter, but notice the diameter's definition. A diameter just isn't something that's a double the radius, because we know a diameter is twice the radius. Okay, but diameter actually is a chord. Okay, think about that. A diameter is a chord. A chord is something that starts and stops on the edge of a circle. Well, if you look at that picture above, doesn't the diameter start on the left side of the circle and go to the right side of the circle? Okay, so a diameter actually is a special case of a chord that passes through the center of the circle. Okay, that's the criteria. It's not just any random chord, because I can make a bunch of different random chords that starts and stops in a circle. Okay, but more importantly, a diameter is one that starts and stops on the circle, but it must pass through the center. Okay, if you have that, you know you have a diameter. Go ahead and pause this screen, Mr. Bergstead, or anybody else in the room, if we still need to write down all these definitions. A couple more. Again, you can probably go ahead and even add these items that you see on the right side on the screen here on the circle. You can go ahead and add these if you want. Okay, you have a secant line, okay, a secant line, and you also have a tangent line, and then you have that little red little dot called the point of tangency. So go ahead and either add those or draw a new circle, whatever you choose to do. Okay, 2 more lines I want to talk about in relationship to a circle. One's a secant line. notice if I were to do this, if I'm going up to my picture, I'm going to ruin it here for a second. If I cross all this stuff out on the outside of the circle, okay, realistically, on the inside of the circle, you have a line that starts and stops on the circle. You have a chord, okay? But as soon as I turn that chord, which is really a line segment, and I turn that thing into a line, it goes infinitely in both directions, I've now turned that into a secant line. A secant line, by definition, is a line that intersects a circle in 2 points. So you can see here on this picture a secant line. This line intersects a circle here, and it intersects a circle here. Okay, and so we're going to call that a secant line. If a line passes through a circle and hits it twice, I'm going to call it a secant line. On the flip side, I have something called a tangent line. Okay, and when a tangent line, you can see actually from the picture, a tangent line is a line that only intersects a circle once. It just barely touches it as it goes by. You can call this one right here, the one I'm circling in, that point B, okay, is where it actually is touching, even though it may look like it's touching more than once. It's only going to touch it once, and we're going to call that a tangent line. So a secant touches it twice, a tangent line touches it once. And then obviously, as you can probably tell, the point of tangency is actually where the tangent line hits the circle. So in this case, I probably should color it red since they have this little thing color-coded. This point B right here, where that tangent line touches a circle, okay, that is where I have a point of tangency, where the actual tangent line touches the circle. Again, if you need to pause this, please do. One thing I want to talk about is the idea of common tangents. Okay, when I go ahead and look at common tangents, you can go ahead and write all this down on your paper right now. A common tangent is a line, a ray, or a line segment, so any kind of the line ideas, that is tangent to two coplanar circles. I'll explain what two coplanar circles are momentarily. And they are called and it's called a common tangent. So if you look at the picture in the bottom left, you can see I have two circles, and it looks like that blue line is tangent to them both. Okay, it looks like the line touches this one, or touches this circle on the left right here, and it looks like it touches this one over here. Okay, we're going to call those a common tangent. It's a tangent line that's common to two or more circles. Okay, similarly on the right, you can see that the blue line is touching here, and it's touching here. That's going to be what we call a common tangent line. Okay, something that touches, or a line that touches two or more circles one at a time. So it doesn't cross through twice, it only hits each circle once. So let's take a look at this. You do not need to write this down. Okay, we're just going to go ahead and work through it together. Take a look. What I want you to do is look at the terms on the left, and I want you to match up the terms with the terms on the right. So if you look at the picture, I want to look at number one. Number one is D. Okay, if you look at point D, okay, I can obviously see it's in the bottom of the bigger circle. Okay, if I look at point D, I think it looks like it's on the edge of the circle. And I also see that it is next to or right on with this tangent line, it looks like. So it looks like there's a point right here, and this line's passing through it and only hitting that circle once. I think I'm going to call this thing a point of tangency. Okay, if I look at FH, I can see that F is tangent, and I can see that H is tangent, so I can see that this line right here is tangent to both circles. And just like the previous screen, if I have one tangent line that is tangent to two or more circles, we call that a common tangent. So I think that is F. If I look at CD, okay, CD, you can notice, okay, it's going to be very tricky. The book's going to try and trick you. You got to pay attention to the symbols. Okay, so right above CD, you see a line segment. So be careful with that because it's going to change your answer based on what kind of symbols above the letters. If I look at CD, so it starts at C, ends at D. So it starts at C, starts at the center of the circle, and goes to D and ends. If it starts at the center and goes to the edge of the circle, I think I'm going to call that a radius. Similarly, if I look at line segment AB, okay, and this is very important, it's not line AB, but it's line segment, so it starts at A and ends at B. If I look at that, it's not the entire line, it's just the piece that starts and stops on a circle. I think I'm going to call that a chord. And if I have point C is something that probably is the easiest for us. It looks like it's the center of a circle, so I'm just going to go ahead and match it up with A. And if I have line segment AD, I'm going to get rid of my previous problem here. If I start at A and I end all the way at D, I think I'm going to call that a diameter. It starts and stops on the edge of the circle, but it passes through the center. And finally, the difference, what about line AB? Line AB, so if I have this entire thing here, it goes infinitely in both directions, it's hitting the circle twice, I think I'm going to call that a secant. There's going to be two theorems that I want you to know. Again, go ahead and pause this. I'll give you a few seconds myself. Okay, but I want you to go ahead and write down this theorem 10.1. All right, theorem 10.1. Theorem 10.1 says in a plane, we know what a plane is. A plane is just a flat surface that goes infinitely in all four directions. A line is tangent, so a line touches the circle once. That's what a line is tangent. A tangent line means. A line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at its end point on the circle. What that means is this. If I think, and I'm going to use a picture here as my example. If I think that this blue line right here is tangent to my circle, okay, the way I can check that, or the way I can either verify whether it's true or false, is whether I take my radius from the center and draw it directly to here. Remember, this right here would be the point of tangency. If it truly is tangent, that's going to be my point of tangency. You're going to see here, if that actually is true, if I actually have a tangent line, when I draw a radius, that same point where the blue line is hitting the circle, and I draw my radius right to that same point, which I'm going to call P, if that actually is true, I know that those two lines right there are going to be perpendicular to each other. If they are not perpendicular to each other, that line is definitely not tangent. Okay, so the point of tangency should be the location where I have a right angle, where I should have that blue line, which is the tangent line, being perpendicular to the radius that goes directly to that same point of intersection. So let's go ahead and use that to our advantage. Okay, take a look at this. Okay, you can go ahead and I want to, instead of having you write all this down, I'm going to have you say this. I'm going to basically ask you whether or not, this is your question, and I'm going to erase it, but you can write this at the very top. Okay, is AB tangent to circle C? Okay, that's going to be your question. Is AB, line segment AB, is it tangent to circle C? So we can go ahead and abbreviate all that stuff on top. Just go ahead and answer that question. This will be problem number 1 on the left, and then this will be problem number 2 on the right. Okay, I'm going to go ahead and erase the instructions so I have a little bit of a room. So let's take a look at this first one. If I want to prove that they're tangent to each other, okay, I know that the tangent line or tangent segment, whatever it is, better be perpendicular to the radius of the same point. So you can see here, if this truly is tangent, it should be perpendicular to that radius. So my question is that actually true? Well, if you take a look at this, I've created now a right triangle. If I go ahead and complete the right triangle, I really have created 3 sides that make a right triangle, and all I have to do is verify whether it's true or not. Well, we know from previous chapters that if it's a right triangle, I'm guaranteed that the Pythagorean theorem works. Okay, I can see that my 2 legs are 3 and 4, so I know 3 squared plus 4 squared, okay, equals question mark 5 squared. The reason why I put a question mark is I'm trying to prove whether or not that actually is a right triangle. If it's a right triangle, then it's perpendicular. If it's perpendicular, then AB is tangent. So we've seen these numbers before. 3 squared is 9, 4 squared is 16, equals question mark, 5 squared is 25. And hopefully 9 plus 16 is 25, and I definitely know that 25 is equal to 25. And so your question is AB tangent? Well, if it's a right triangle, and if the right triangle has a right angle, if that's a right angle, then definitely that's perpendicular. Okay, and so therefore my answer is yes. Okay, definitely. AB is definitely tangent to BC in this picture. Okay, now again, if you need to grab calculators at this point, please do, because they're not always going to be that easy. What about this one over here? Again, I want to see if this is a right angle or not. Okay, you can see that my two legs then, if the truth truly is a right triangle, are 3 and 6. So I'm going to do 3 squared plus 6 squared, leg squared plus leg squared equals question mark 7 squared. Now I have 3 squared, which is 9, 6 squared, which is 36, equals question mark 7 squared, which is 49. If I go ahead and do this, I have 9 plus 36, and 9 plus 36 should give me 45. Does definitely not equal 49. So I should tell you something. Is AB tangent to BC? Well, my Pythagorean theorem didn't work. If my Pythagorean theorem didn't work, that must mean that I don't have a right triangle. If I don't have a right triangle, I don't have a right angle. And if I don't have a right angle where I have it marked right now, then it must mean it's not tangent. So my answer right here is absolutely no. Okay, what about this? Go ahead and I'll give you a few seconds. Please write down this whole instruction on top. It says in the diagram, line segment AB is tangent to circle C, so I know for sure it's tangent. Therefore, you can see they put the right angle in there. At point B, find the radius R of circle C. Go ahead and write this down. All right, I know that AB is tangent to circle C at point B, and I want to find the radius. So I definitely know I have a right angle here, so if I have a right angle here, I know I can use a Pythagorean theorem. But I have to do a little bit of legwork in first. I know that my two legs are 12 and R, because those two legs are the ones that touch a right angle, so I know I can have those two as my legs. But then my question is, what is my hypotenuse? Really, from here to here, you have an R and you have an 8. Now remember, we're not going to multiply those together. Those are two single pieces that I can add together to get the entire length A to C. Okay, so instead of saying 8R, which is not right, you never multiply those numbers together. Okay, I can say it's really R plus 8. Well, that's going to be fine. We can handle that, because now let's try and put that into Pythagorean theorem. If I do that, I really have R squared plus 12 squared, the two legs, the ones I have circled, R squared plus 12 squared, equals the entire hypotenuse squared. Well, the entire hypotenuse squared is R plus 8. Now you gotta depend a little bit on your math skills from algebra. Okay, I still got over here, I got R squared plus 12 squared, should give me 144, was something that we should know, one of those perfect squares through 15, we gotta know 12 squared. Okay, but then what about R plus 8 squared? We have a binomial squared. I think from last year, when you learned this, you would do this. You do R plus 8 times R plus 8, okay, because it's two of them sitting right next to each other being multiplied together. And then you would FOIL. Okay, that's important. First, outside, inside, last. Okay, so let's go ahead and do that. I have R squared plus 144 equals. Okay, first times first. R times R should give me R squared. Outside, R times 8 should give me 8R. Inside times inside, 8 times R is 8R. And last times last, 8 times 8 is 64. Now it's just a matter of going ahead and cleaning up all the mess. So I still have R squared plus 144 on the left side equals, I think I can combine those two R's. So I have R squared plus 16R plus 64. Now I just got to start combining stuff left and right. The cool thing is I see R squareds on both. Okay, so if that's the case, if I were to subtract r squared, because there's a positive r squared, so if I subtract r squared from both, okay, notice what happens. Okay, all of a sudden those cancel out, but then I also have a 1r squared minus a 1r squared. They also cancel out. That's actually convenient, because now I have 144 equals 16r plus 64. I think then most of us would probably subtract 64 from both sides and go ahead and take out your calculators. When you subtract 64 from both sides, hopefully you guys are getting 80 equals 16r, and then divide by 16 on both sides. I think I get r to equal 5. Okay, so when I have that, I think I go back and reread my question. My question was to find the radius r. In this case, my radius is 5. One last theorem I want you to do. Okay, go ahead and pause this. I'm going to go pretty quick here. Okay, go ahead and pause this when you need to. But theorem 10.2 says this. Tangent segments from a common external point are congruent. So take a look at the picture. Do you agree that from S to R, this is a tangent segment? Okay, if I were to keep going, it's only going to touch a circle once at R. Similarly, if I draw an S to T, it's only going to touch a circle once right at T. What it's saying is this. If those segments originate or start from the same external point, in this case the point is S on the outside, external means on the outside, okay, if they start from the same point and go to the same circle, I know that those segments have to be congruent. So in other words, SR has to be congruent to ST. That has to be true. So again, pause this, write this down. The one example I want to do that, actually two examples I want to do that, is this. It says that JK is tangent to circle L and at K, and JM is tangent to circle L at M. Okay, and so you might want to write that down, the fact that you know that JK and JM are tangent to both circle L at M and K, and I want to find the value of X. Well, if I look at, let's go ahead and just isolate just one of the problems at one time here. I'll give you a few seconds to go ahead and write this one down. Well, what do you know? If I know that J to K is a tangent segment to circle L and J to M is a tangent segment to circle L, and they both originated or both started at point J, I think I know that JK has to be congruent to JM. So in other words, I should know that 5x minus 4 is equal to 2x plus 2. Okay, those two segments are congruent to each other. If that's the case, I'm going to go ahead and subtract 2x from both sides. This is algebra we should be pretty good at by now. 3x minus 4 equals 2. I'm going to add 4 to both sides. That goes away, so I have 3x is equal to 6. Divide by 3 on both sides, so I get x is equal to 2. When I look back up my problem, I can see I just simply asked to find a value of x. I've got it. I'm done. Don't go ahead and write this. Don't write this one down. Let's just go ahead and do it together. If I look at this, I can see again that J to K and J to M are tangent to the same circle, and they're both starting at the same point J. So I know that those two segments have to be congruent. So therefore, I have 3x squared minus 10 is equal to 17. I think most of us would probably add 10 to both sides. So now I have 3x squared is equal to 27. Now, I want to get x squared by itself. It's being multiplied by 3, so let's divide by 3 on both sides. So I have x squared is equal to 9. And now I want to get this x by itself. It's being squared. The opposite of squaring is taking the square root of both sides. So I get x equals 3. Okay, you should know 2 theorems today, as long as all those different definitions, 2 different theorems, okay, that you wrote down, theorem 10.1 and theorem 10.2. Good luck over the weekend, and here is your homework. I'm looking forward to see you guys on Monday, and we'll pick up the pieces then and make sure you're set to go. Have a good weekend.